Okay, so on Wednesday, we went through a review of integration in one dimension. The reason being that we're moving that into more than one dimension today. This is the only short section that we have on integration in this course. There's a few applications that we can use integration in more than one dimension for. When we're working out, say, the volume of a solid, that's really the key thing we'll be focusing on in this course. And we'll go through today working out the area of, the volume of a solid using cross-sectional areas and estimating those. Say if you've got something like a log or an organ and you want to work out what is the volume of that solid, we can estimate it using cross-sectional areas, and a similar idea to what we did with our Riemann sums before on Wednesday. And the other thing is volumes of revolution. So where you have, say, a curve or two curves that define some area, and then you rotate those 360 degrees in one direction, and that gives you a solid that has rotational symmetry. So we can use our understanding again of cross-sectional areas, but now thinking about rings or circles, and then we can integrate over those or estimate those to give us a volume for that solid. Okay, so I'll just summarize the pre-lecture material. So the pre-lecture material started off with this discussion of laminar flow, so blood flow through a vessel. How do we work this out? We've got an equation for our laminar flow at a particular point, so at a particular radius from the center. We can analyze this problem by breaking it down to lots of small rings. And in thinking about the flow through a particular ring, we can then think about combining all of those little rings up, and that will give us essentially the flow through all of the rings together. Okay, so we're adding up all these little pieces, and that's kind of the same idea as we did the other day. If we break a problem down into little pieces, we can add them up to get, on Wednesday's case, small slivers to give us areas. Here we're going to be adding up those small slivers of areas to give us volumes. Okay, so that was the key idea here. The math was a little bit involved here, but it's the same basic principles of integration. Okay. The lecture then went on to talk about thinking about areas under or volumes under a surface. So when we had a curve that would give us an area underneath that curve. When we've got a surface, we think about the volume underneath that surface. And just like with our one-dimensional cases where we would break it up into lots of different rectangles, here we're going to have these rectangular blocks, and we're going to think about volumes instead. So the same principle applies. The more blocks that we have, the better our approximation is going to be. So if you have this kind of case on the left-hand side, it's not going to be a very good approximation because you've only got 4 blocks. As you get more and more of these blocks here, you get closer and closer to that surface. And that's essentially what's happening when we do our integral. We let these number of blocks tend towards infinity. So the width and the length, if you like, of those blocks are getting smaller and smaller and smaller. We end up eventually getting our integral. Okay, so this is our double integral here. This is a definite integral because we have these limits. So the key thing with these limits to remember whenever you do an integral, if you're doing the exact double integral here, is that you do the internal part first. So think of this as being in brackets here. So these integrals here should be for our C and D, and the A's and B's should be for our Y. Okay? Well, that doesn't make sense here. Hold on a sec. That looks a little bit sketchy. I think these might be around the wrong way. The X's were the A's and the B's, and the Y's were the D's and the C's. I'll correct that afterwards. Okay? But we should be matching these things up. Make sure your X's are matching up with your DX's and your Y's are matching up with the DY's. Okay, so there's an example of a double integral, but I really want to focus more on these cross sections and thinking about having a solid that we're going to be slicing up. Think of it as a loaf of bread, and you're slicing up that loaf of bread to get these individual slices. You can work out the cross-sectional area of that slice. And then if you know the width of that slice, you can work out the volume of that slice. Guys, can we cut the chatter a little bit? Thanks. So you have the volume of that slice, and then we're going to add up lots of those little slices, and it will give us the volume of this loaf of bread, okay? And the same applies if we're doing a loaf of bread or an organ, okay? So think about these as individual slices of bread. That might be a good way of visualizing it. Okay, so the if we make those slices of bread thinner and thinner and thinner, to the point where they're infinitesimally thin, we're just going to get the area, the cross-sectional area for a particular value of x, if x is our varying the length of our solid, okay? So we have this cross-sectional area here, this A of x, and if we integrate over all of those, rather than having this finite sum of different cross-sectional areas and cross-sectional volumes, we're going to end up with our integral, okay? So as we take the limit of the number of slices that we take, n getting very, very large, the width of those slices gets smaller and smaller and smaller. In other words, this delta x gets smaller and eventually turns into this dx and a definite integral, okay? So on Wednesday, rather than having areas here, we had essentially heights of under our curve. And because we were integrating height is at just a length, when we integrate a length, we get an area. When we integrate an area, we get a volume. Okay, so you're just increasing the dimensionality by 1 when you do these things. The form of this, though, looks basically the same as what we did the other day. Okay, it's just now we've got an area rather than a length or a height. Okay, there's this example of volume of a liver. So if we have some solid and we don't have a formula for what is the curves that define this solid, but we have estimates of cross-sectional areas, we can use our midpoint rule that we used the other day, but rather than doing heights, we're now just treating these as areas. So previously, we had height of our function on this y-axis here. Now we've got areas, but the method is exactly the same, okay? So rather than, essentially we have each of the area of each of these rectangles, we have a delta x, which is the width of that rectangle. So because we're taking a width times by an area, that gives us a volume, okay? So when we sum up all of those volumes, that gives us the total volume here. Again, the method is essentially the same as what we did in one dimension. It's just now we're dealing with areas times by a width rather than lengths times by a width. Okay, so the dimensionality has gone up by 1, but the process is the same. Okay, the key thing that people tend to struggle with when it comes to integration, or in this course at least, with integration more than one dimension, is volumes of revolution. So I mentioned at the start this idea of rotational symmetry. If we have some here, for example, if we have this area, so we've got a two-dimensional area that's here defined by some limits, some x and some start and some endpoint in the x dimension. It has some curve which is an inner radius, has some curve which is an outer radius, so it's just some area, and we're going to rotate that shape 360 degrees, in this case around the x-axis. Okay, that ends up giving us something like this. I tried to sketch it out in green here, essentially what's going on. We're just taking that, flipping it around 360 degrees, and that gives us this solid on the right-hand side. So because there's nothing in this middle bit here, we end up with this hollow. Okay, so this is how we can get things like washers. So a washer is just something that looks like this. It's where you've got an outer, you've got a ring, basically, that's got a hole in it. So I think a donut or a washer. We do exactly the same process, though, in the sense that we're thinking about these cross-sectional areas. And then we take a delta x, its width. We take that cross-sectional area, we multiply it by its width, and that will give us the volume of this washer. And then as we take the width of that washer to be smaller and smaller and smaller, our sum turns into an integral. So how do we work out the integral for a volume of revolution? We need to think about the volume of, well, first of all, work out the area of this ring. Okay, so the area of this ring, well, the area of the outer ring is going to be pi r squared, where r, let's call it r out, pi r out squared, so that's the outer radius. But it has a hole in the middle. So we need to subtract the area from the inner part that we've cut out, okay? So imagine you've got a circle that's filled in, and you're going to punch out a middle circle to that. So you're taking away that area, so we need to subtract this inner radius here. So we do pi r out squared minus pi r in squared, where r in is the inner radius, and that will give us the area of that washer, okay? Just that face of this washer here, okay? We multiply that by our delta x, our width, and that will give us the volume of that washer. So when we integrate this and that delta x gets smaller and smaller and turns into a dx, we need to take the integral of pi on the outside, that's just a constant, so it can come out, it doesn't need to be in the integral, of our outer radius squared minus our inner radius squared, okay? This ultimately gives us the volume of this solid as we integrate from A to B, if this was our A and this was our B. Okay? That was about it for the pre-lecture material. Yes, question?
What is rotation? Just finding the area of volumes.
So finding the, so here it's just defined by this, this cross-sectional area here at the bottom. The problem with just trying to estimate this by the areas is you could do it if you're saying, okay, I'm going to work out these different areas here, but it's hollow in the middle. Okay, so this is a bit of a problem if you're trying to work it out just by estimating these cross-sectional areas. You could do it and then subtract the middle part. It's a little bit nicer to do it if you know something has rotational symmetry, you can use this idea of you can use that rotational symmetry to work out the area of those different washers and then integrate over that. So it's an easier way of doing it. You could break it down into lots of different bits and then try and add all of those different bits up.
Not exactly.
It is exactly what we're doing in a sense of how do we get from this mathematically to this? We're adding up lots of different small areas. But if are you trying to say, why don't we just add the things up rather than do the integral? The idea of rotation is that we can use pi r squared to work out our areas, okay? Rather than breaking it up into lots of different rectangles. So if you imagine if you were viewing this side on, if you had a solid that was like this side on, but it was hollow in the middle, like this. So this area here doesn't exist. You'd have to break this area, you'd have to work out this area here, and this area here, and this one, and so on. You'd also be missing out what's going on, because it's rotational, you'd be missing out what's going on this side here. So in theory, you could probably break this down into a smaller problem, but it's much easier to think of it as rotational. Okay. Any other questions? Okay, let's go through some problems. Okay, so I'm going to start by just summarizing what we're doing again here, just to review it. So we're told here, suppose S is a solid, and we know these different cross-sectional areas of this solid. Okay, and we're going to try to approximate that solid using a Riemann sum. So just like we did the other day, but now with areas rather than heights or lengths. And then we're going to write an exact expression for the volume, okay? So what does this look like? Imagine we've got solid S. We don't know what shape it is. It could be something like this. I'm just going to view it from the side. This is my side view. And because we're going to approximate it using Riemann sums, we're just going to break it up into these rectangles of equal width. And suppose we're doing a midpoint rule. Each of these rectangles, the top height would be given by the top curve, where the middle of the rectangle goes through that top curve. And the bottom would be where we have the bottom of the rectangle intersects with the bottom curve, okay? So this is a bit like when we were doing our leaf example that was in the solutions from Wednesday. You take the top of that rectangle is defined by where we have the intersection of the midpoint with the top, and the bottom part is the bottom curve with the intersection of the rectangle in the midpoint again. Okay, so we have all of these different things. We're now going to think of these as areas. So call this AI plus 1, and so on. And each of these different areas, we now have a width of delta x. Suppose we're going from some limits, we don't know what they are, so we're just going to call them x is equal to a and x is equal to b, so some start and some end points. So just to make sure it's clear, each of these different rectangles that I've drawn here, because we're doing a side view, these are projected out into that direction, okay? So out behind the screen. These aren't two-dimensional things. We're just viewing it from the side. So that's why we have an area here, because we're thinking about the area in that direction, okay? So it's not the area, these AIs are not the area of this rectangle here. It's not the area of this rectangle here. That's what we did in one dimensions. The areas that I'm talking about are the areas, if I view it from, say I view it from the front, and it looks like this, I'm thinking about this area here, okay? I'm viewing it from the side, and each of these AIs is the area of those slices there, okay? So it's not the area of these rectangles, it's the area of the slices. And we're given those slices, we're told we know what those slices are. So for example, if you do something like it, if you have a CT scan or an MRI, it's taking slices through from some sort of tissues, and then you could work out what the area of each of those slices are, okay? So the area of these slices, we have these delta x's of the widths of these slices, or if your CT scan is not continuous, say it's taking measurements at various points, you could just take the distance between those measurements as an approximation for our Riemann sum, okay? So if we want to work out the volume of this solid, our total volume is going to be approximately equal to the sum of all the individual volumes. So if we have n different slices and different measurements, and I call these volumes VI, okay? What is that VI? Well, it's just going to be the width of that slice. Think of these again as slices of bread. So it's the width of that, the thickness of that slice of bread, times by the cross-sectional area, AI. And we're going to sum over all of these from 1 to n. Okay, what happens if n gets really, really large? Well, in other words, if n gets really, really large, we're having more and more slices. So we're going to be breaking this down into smaller and smaller slices of bread, if you like. And so delta x is going to tend towards 0. And it turns into this dx, so we get our integral. So our exact integral is going to be the integral from a to b. We knew this a of x, an equation describing the cross-sectional area at point x as we move along in the x direction. So this is the x direction. We pick a point x and we work out the cross-sectional area at that point x, okay? This is our integral of our area is going to give us volume. Okay. Recap the solids of revolution. What would we do in this case? Well, suppose we've got solid. I'm going to do it a little bit simpler here and not have a hole in the middle. Okay, so this is going to be something that's a solid. Think of it as being maybe a stone or something like that, but it's got rotational symmetry. And suppose the profile of that stone looks something like this. And again, we've got some starting point and some end point. X is equal to A and X is equal to B. And this is rotated around this x-axis here. Okay, so we have this profile. Imagine this is the bottom of the stone, and we rotate that round, and that'll give us the entire stone with rotational symmetry. Okay, so it's now solid in the middle. This is like the example in the pre-lecture where I've just discussed, where we had an R in and an R out. So there could be something here, like another curve, that would give us a hole in the middle. But for here, I'm just going to say there's no hole in the middle. Okay, so it's bounded by this x-axis and by this curve. And when we rotate it, there's no hole in the center. Okay, so we want to find the cross-sectional area. So we take a slice through this thing here. And again, we want to work out the area, not of this rectangle that I've drawn, but we're working out the area going into the screen. okay? So our delta x is going to be this width here, but our area, our AI for this particular slice is going to be the area, the cross-sectional area going in this direction, going into the screen. So again, if we were to view this side on, you'd maybe have an object that looks like this. That's not rotational symmetry. Let's do something a little bit better than that. Slightly better. Okay, if this is the front view of our stone, we're working out what is this area here, not what is this area here. Okay, just make sure that's clear. So what is the area of this? Well, when we rotate this around, we're going to have a circle. Okay, so just like I drew there, we've got a circle at the, and we're going to have all of these different circles. So as we vary the x location, we're going to have circles that have different radius. So in the middle, maybe it looks something like this. That's the circle here. If I took this one here, something near the end, maybe my circle looks more like this. Okay, so the radius of this circle is varying as we move along the length of this object, and therefore the area of the cross-sectional area is varying as we move along. Okay, so again, if you've ever seen footage of like a CT scan or an MRI where they go through an organ and it varies, and you see this movie as it's going through and it's changing, that's essentially what we're doing here. We're taking lots and lots of little slices, and as you move through that, the cross-sectional area is changing. Okay. So if this cross-sectional area is changing, we want to work out what is that cross-sectional area. Well, because it's a circle, we just need to, the area of the ith one that we're choosing at some arbitrary point is just going to be pi r of xi. So this r of xi, I'm going to define this curve as being r of x. Okay, so this is the curve that is just defining the outline. So the cross-sectional area is going to be pi r xi squared. Okay. And because this curve is r of x, this r of xi, I'm just going to choose to be, we'd usually choose it to be the midpoint. So I'm going to, for argument's sake, I'm going to put this as my xi. And this r of xi is then going to be the distance from the x-axis down to that curve. Okay, because we're rotating this round and we're rotating into the screen and back around again, we have a radius which is given by this curve, and as we rotate that round, that gives us a circle. So that radius for that particular slice is going to be defined by the length from the center to the outside of this curve. So that's r of xi. We do pi r xi squared, and that gives us the area of that circle. And then if we want to work out the volume of that the little slice, you can think of these maybe slices of salami now. It has width delta x, its cross-sectional area AI. So that gives us the volume of that slice. So we can say in this case, our volume is going to be approximately equal to, again, our I is equal to 1 to n of our VIs. So just like above, we're summing all of these things up. And so we end up with the same formula here to start with, our delta x times by AI. So this is the same as this, because we are just summing up those areas to answer your question again from before. It's the same process of doing lots of little sums. But here, now that we take our integral, we can take advantage of that rotational symmetry. So here we just had some a of x, okay? So we needed a function to describe what was going on for the area at that point. Here we actually know what that function is because we have rotational symmetry. So we know the area is going to be this pi rxi squared. And because we're taking n tending towards infinity, so our widths get smaller and smaller and smaller, that delta x turns into a dx. And so we can think about our rx now, that curve that defines the outline, times by dx. that we have that Rx squared. Okay, so we've got pi Rx squared, again, by R of X, that is. So the X coordinate, the radius of the X coordinate squared, times by pi, integrate between these limits, and that gives us the area, the volume, sorry. So yeah, just to reiterate, going back to that question from before, we are essentially doing the same process here, but we know the formula here. That's the key difference. Because we know that these are just circles, we can take advantage of that rotational symmetry to know what the formula is. Whereas if we just had a generic solid like this, we don't necessarily know what the formula is to describe the outlines. We can't take advantage of that rotational symmetry. Any questions about those things that I know I've kind of labored the point a bit about rotational symmetry, but people in the summer struggled a bit with this point, so I wanted to make sure it was gone through in detail. Okay, let's think about an example and where we want to estimate the volume. So here we've got some cross-sectional areas. So someone's taken slices through a log, and they've made these measurements of what is the cross-sectional area at these different points. So they've taken these slices through at 1 meter intervals. And then we've got the area in meters squared at these different points. Okay, so we've got these slices of a log. And we want to say, okay, well, can we estimate what the total volume of this log is from those cross-sectional areas? Okay, so what does this actually look like? Well, we can think about our areas at particular heights, or particular lengths, sorry, along this log. And we could just plot these values, okay? And this is just like if we were doing our, if we were estimating the area under a curve, we're now just doing area, rather than estimating the area under a curve, we're doing the volume under a surface, essentially. So we can plot these different areas here. So here, for example, when X is 0, we've got 0.68 meters squared. And then as I move along, these don't have to be exact. I just want to give an idea of the profile of what this log looks like. Something like this. Yeah, the exact thing doesn't matter. It gives you an idea of the outline of this log looks something like this, maybe, okay? So we can sketch these different values. Of course, I've joined up these dots, but we don't know it's exactly like that. It could have, it could have a branch coming out here that I'm missing, but we can only estimate it based on the information we have. Okay, so we have all these intervals here. So let's draw these on. So this is 1, 2. Let's see, we've got 10 of these. 10, 9, 7, 6, 5. I'm going to put that as my 3. That was my 2. There we go. I missed one out. 4, 5, 6, 7, 8, 9, 10. Okay, these are my different measurements. And we're asked to use the midpoint rule with n is equal to 5. Okay, so because this is a log that's 10 meters long, I want to break it up into 2 meter measurements. So I'm not going to use every single one of these here. I'm just going to use 2 meter intervals. And that will give me 5 different areas. Okay, because we want our n to be equal to 5. Okay, so I want to take chunks along here at 2 meters, 4 meters, 6, 8, and 10. And the heights of these, because we're using the midpoint rule, the height is going to be determined by the midpoint. So the height at 1 meter, 3 meters, 5 meters, 7, and 9, and so on. Okay. The height of this function, and this function is our area. Okay. So we've got a rectangle that looks like this, and this, 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 and this. So we've got our 5 rectangles. We can call these A1 to A5. Okay, so the last thing we need here is because we've got a length of 10 meters and we've got 5 of these areas, our delta X is going to be 2 meters. So what I've done here is I've taken the heights of these are going to be at 1 meters, 5 meters, 1, 3, 5, 7, and 9, sorry. Okay. These are going to be areas that I'm going to use to estimate the total volume. The volume is going to be a delta X, approximately times by the sum of these areas. We just need to add these up. Okay. If you do that, it should come out to 5.8 watts. What are my units here? I'm going to pick on someone over here because I never heard from you guys. What are the units here? Yeah. Meters cubed, great. We're doing volume here, our width, our measurements along the X direction were in meters. We had meters squared, so we end up with meters cubed, okay? So just to really make sure it's clear, these areas that I'm talking about here, I'm representing area as a function in one dimension here, right? But I'm not talking about the area of this rectangle, okay? I'm talking about the area here is represented by this height, okay? So I've labeled this as A1, but really the A1 is there, the A2 is there, the A3 is there, the A4 is there, the A5 is there. And the actual, those rectangles here, because we've got an area times by a width, this is really my V1, V2, V3, V4, and V5. These are my volumes, okay? And we're adding up those volumes. So what we've done is, from the case from the other day, we've just increased the dimensionality by 1. So that's why we've gone from areas to volumes. Okay. Let's think about a volume of revolution case. Okay, so we've got this region bounded by the axis, and we're going to the x-axis, and we're going to rotate it around the x-axis. We're going to rotate it in this direction here to form a solid. Because we're bounded by the axis here, there's not going to be a hole in the middle. We don't have a function describing what is this. We don't have like an f of x or an r of x that we had in our previous example. We talked about this as an r of x, this curve here. We don't know what this is. Okay, so we're going to have to estimate this. And we're asked to do this using the midpoint rule with n is equal to 4. So we want to break this into 4 equal chunks. And we're going to rotate this around. So use the midpoint rule, just like we did the other day, to estimate the different heights of this function. The heights of that function are then going to give you your cross-sectional areas when we do a rotation around the axis, okay? So just as a reminder, our total volume is going to be our delta x times by pi times by the sum, I is 1 to n, of our radiuses squared, our radii squared, I should say. Okay, so first estimate what are the different radii that you're going to be using. We're going to have 4 of these. We're going to break the solid into 4 chunks. And think of breaking it down into 4 different rectangles. And then you're going to rotate those rectangles around the axis to work out what is approximately the volume of this solid. Okay, so have a go at that. Okay, let's see how you guys got on. So we're going to break this down into 4 chunks. So I'm going to break it down into rectangles with sides at these points here. We're using the midpoint rule, okay? So that means that we want the height of my rectangles here to be determined by the middle point, the middle point along our rectangles in the x direction, okay? So the points at 3, 5, 7, and 9. So if I draw those points on here, the height of my rectangles is going to be determined by each of these points here. And I can sketch them on, okay? So when doing this, you might find it easiest to, like I've done there, to first of all put on your dotted lines or dashed lines to indicate where your limit's going to be, find the midpoint, and then just go up from the midpoint to the curve and then draw your line across, rather than trying to draw the line across and try and get to estimate where it's going to be, okay? So I usually find it easier to draw the point and then draw the line through the point. Okay, so what are these going to be? You're probably going to get different numbers to me, but we've got something. Remember, we're talking about radii here. So the first radius, R1, looks about 1.5. The second is maybe 2.1. The third, let's call it 3.8, and the fourth, 3.1. My delta x here is altogether. Let's try it again, altogether. There we go. Okay. We don't actually have units on this question, so we don't have to worry about units. So what's our volume going to be? I have it written above, so I wrote it out again. We have our, oh, that's where my 2 comes. Sorry, I was a little bit confused. I was just wondering where my 2 came from. Obviously, it comes from the fact we've got a delta x. So the delta x is 2 times by pi times by the sum of our ri's squared. So note that we square our radii individually and then sum them up rather than summing them and squaring them, okay? So that means we need to do 1.5 squared plus 2.1 squared plus 3.8 squared plus 3.1 squared. Again, you might have slightly different numbers as long as your method is the same, that's fine. If we work this out, it's approximately, from my case, 193 units cubed. You might have something that differs a little bit to me, okay? Have a show of hands, you got something in that ballpark? Fantastic, well done. Okay. This one here, I'm going to leave as an exercise for you guys. I'll obviously post the solutions. Here, we're going to rotate exactly the same shape, but rather than around the x-axis, we're going to rotate it around the y-axis. So we're going to rotate it in this direction here. And that means that there's going to be a hole in the middle of this solid, this area here that I'm coloring in. It's going to be hollow. So that means you need to estimate the radii from, say, here to here. Again, use the midpoint rule, split it up into 4 chunks. Now we need to account for that hole in the middle. So you need to basically the same process, but subtract the volume of that hole in the middle, which is determined by that inner radius, okay? So have a go at that in your own time. The reason I want to skip over that here is because I want to talk about this problem at the end, which is a little bit more complicated. Okay, so here we've got an example where we want to estimate what's the volume of snow around the trunk of a tree. A little bit of quiet, guys, thanks. So we're going to suppose that this area around the trunk is rotationally symmetric. We're going to use our what we know about rotational symmetry to work out the volume of snow under this tree, okay? So we're given this function here. It tells me what is the width based on the radius at a particular point, okay? So we've got the distance from our trunk, and we've got our depth here. So what we're going to be doing is we're going to be making slices, start off with, that look like this. And then we're going to add up all those slices just like we have before. So if we want to know how much snow is on the tree, it's the snow that's not in the hole. That's the way of thinking about this problem. There are a couple of different ways in which you can do this. The first method is going to be using volumes of revolution. So this method 1. And actually what I'll do is I'm going to turn this diagram on its side. Okay, because we're rotating around this direction here, it's easier to think of it when we flip it round on its side. So what does that look like on its side? It looks like this. So now we've got our W going here. We're going to call these W and R. And we're just flipping this on its side. So if we copy over the intersections, our curve now looks like this. So all I've done is I've taken this curve here and I've flipped it around on its side. Okay. We were told that up here, W is equal to R squared minus 3 squared. So we can rewrite this for R, okay? So we can take the 3 squared over to the other side, that's 9. So R squared is equal to W plus 9. So R is equal to square root of W plus 9. So what we're doing is we're now taking slices like this, and then we're rotating it around this axis here. This is just what we've done, right? We've got rotational symmetry, we've got a curve, we have an equation for that curve. R is equal to square root of W plus 9. That gives us the radius at a particular point. Now we can work out what is the volume based on that radius, okay? So what is our cross-sectional area at width W? Just gonna put my bounds on here. This goes through -9 and 3. Our cross-sectional area, guys, can you have a little bit quiet, please? Okay, our cross-sectional area is going to be pi r squared. And we know what our r is because we're given an equation for it. Okay, so we had an equation for W in terms of r. So we can get r in terms of W just by rearranging. And then we just substitute this in here. So our cross-sectional area at a given point W, as we flip this on its side, it's going to be pi r squared. R is the square root of W plus 9. So R squared is just going to be W plus 9. And from here, we work out our volume just by taking the integral. Because we've got a formula for our area at a cross-sectional area at a particular point, we can work this out exactly. We don't have to estimate it. We're going to go from -9 to 0. -9 because this is -9 here, this point at the bottom of our hole underneath the tree, our hollow. And 0 is so this -9 is -9 meters, is it? Like measured in meters? I can actually say. I'm going to assume it's meters. That's quite a deep hole. Feet, is it in feet? Thank you. That makes way more sense. Again, stupid units. I work in meters. Okay. So we have our area at a point W, and we're integrating with respect to W. Now we just need to substitute in our A of W from above, which is just this line here. So the pi is just a constant, so it can come out the front. This is a definite integral from -9 feet to 0 feet of W plus 9. So this is just a nice one-dimensional integral, even though it's a problem with 3 dimensions, because we're working out a volume. We can work it out just using that rotational symmetry, which means that we don't have to think about double integrals here. We can just think about one integral. So we integrate this. We now have a half W squared plus 9W evaluated between -9 and 0. So if we substitute these things in here, we have pi times pi 0, 0 plus 0, minus W squared. So W for our second part is going to be -9. So -9 squared is 81. Divided by 2, plus 9 times by -9. So plus minus 81. Which gives us 81 pi over 2 feet cubed. Okay, so we're able to break down this problem by flipping it on its side, calculating the radius, and then rotating it around. Yes. How do I get the half in front of here? So we're integrating this W. So when we integrate W with respect to W, we increase the power by 1, so we get W squared, and we divide by the new power. Yeah. Okay. There is a second method for this, which I'll post online, where we break this down into cylinders instead. It's just another way of thinking about the problem. Okay, I've got office hours now. So if you don't need to come and see me afterwards and you can see me at office hours, please do that. Okay.